This conference will now be recorded.
So good evening, students. Today we'll be learning a very important topic in this chapter of waves. This is very important because there are questions in any competitive exam from this particular topic, that is Doppler effect. So Doppler effect is very important topic. You will get at least one question on an average in some of the other competitive exam. Okay, so we'll learn it very nicely and try to remember the formulas related to various conditions. So what is Doppler effect? Actually, this is a very natural effect, like very common natural effect, natural phenomenon we have come across with sound wave, but it is a wave phenomena, so it can be applicable for any kind of waves like electromagnetic wave, magnetic wave, which does not require any medium like visible light, radio waves, microwaves. I'm sorry, radio, not radio, microwaves. In fact, it can happen for radio waves also, microwaves. And which is very common and familiar to us is the Doppler effect in sound. Okay, Doppler effect in sound is very common phenomenon. I'll just give you an example before I define what is Doppler effect. I'll just give you an example, very common example. See, when a fire, like a car from fire brigade, okay, fire car or an ambulance, it sounds a bell, or in case of ambulance there is a different sound obviously. So when the ambulance or this kind of fire car, they ring the sound, and they are in motion. So what we observe, when the ambulance or this kind of fire car is coming far from, like coming towards me from far, then we see the pitch of the sound appears to increase. Pitch of the sound appears to increase when the fire car or ambulance is coming towards me, and when it goes away, then the pitch of the sound becomes gradually lower and lower, and sometime you will not be able to hear. Same thing if you are sitting in a station and a train is passing the station, or in fact passing you. When it comes okay, when it comes towards you sounding whistles, suppose you are sitting in the station, so what you listen, you will be listening that the sound is gradually, the pitch of the sound is gradually increasing. Okay, gradually increasing. As the train goes away from you, then you'll see gradually the pitch of the sound decreases. Okay, pitch of the sound decreases. Okay, so pitch of the sound increases and decreases means what? That is the frequency, apparent frequency increases and decreases. Okay, let us see now scientifically what we are saying about Doppler effect. This is the example. So this apparent change in the pitch or apparent change in the frequency is actually called Doppler effect. How it arises? It arises due to relative motion. It arises due to relative motion between the sound source of sound and the observer, and sometimes if the medium also has some velocity, if it is not still, if it is velocity, then there is a relative motion between source, observer and the medium also moves. Like sound wave needs a air medium, right? In the air medium, if the air also blows, then there is a relative velocity or relative motion between the medium, between the source of sound, between the observer, and in that cases apparent frequency will be hard by the or apparent change in the frequency will be hard by the observer. See in this figure, see suppose this is a fire car. It is stationary. If it blows the horn or ring the bell and you are also stationary, then look, this is actually the wave phenomena. That's why this is sound wave, suppose, and you can see the wavelength of the sound is actually uniform. It is actually the wavelength of the sound you receive is the same as the source is emitting. That means there is no change in the frequency when both of you are stationary, both this source of the sound and the observer are stationary. That means when no relative motion, when no relative motion, then no change in the frequency, no change in the frequency, or not change in the pitch. Okay, but when look, this car, this fire car is actually moving towards you. Look, this wavelength over here and wavelength over here, wavelength decreases. That means the frequency, if it is frequency, or I'll just go with nu prime, the frequency is nu prime over here and here it was nu, then obviously you can see that nu prime is greater than nu. So this apparent change in the frequency is called the Doppler effect. Okay, I'll now define. So whenever there is a relative motion between source and sound, the observer source of sound, the observer and the medium, the frequency of sound as received by the observer is different from the frequency of the sound emitted by the source. Okay, so the apparent change in the frequency of sound waves so the apparent change in the frequency of sound, let us not write the wave, sound when there is a there is relative motion, or in other words, we'll write when the source of sound when the source of sound, the observer and the medium are in relative motion. It's called the Doppler effect. So this was first observed by Doppler, so that's why the name goes with the discoverer or inventor's name. So I have already given the example that when a train is coming towards you, you are sitting in the station and the train is blowing the horn while coming towards you, the pitch of the sound will be increasing. And you are sitting still, and if the train goes away while blowing the whistle, you will see, you will actually feel that the pitch of the sound is decreasing gradually. So this relative change in the frequency of the sound is called Doppler effect. So this Doppler effect actually, see, as I said, it will be observed in case of sound wave. This is actually very much common and actually detectable by us generally, our natural detector. But in case of electromagnetic wave, so what you will see actually, due to Doppler effect, there will be change in the wavelength, like there will be red shift, blue shift, etc. Okay, red shift, blue shift, etc. That means the frequency will be either, sorry, this is frequency or wavelength. In terms of wavelength, we can say wavelength will be either decreased by some change, that is delta lambda, or decreased by delta lambda. So if it is decreasing, this is called blue shift. That means wavelength is actually getting shifted from the original wavelength. The light was coming from some source. Okay, suppose the sunlight coming from, or the white light coming from any source. If there is a Doppler effect in that, so in that case, see, wavelength gets changed. So if the change is in the, like, change is such that the wavelength is decreasing from the original wavelength, then it is called blue shift. And if it is increasing, then it is called red shift. It is called red shift. Okay, this is called red shift. And in this case, one more thing here, I have written with the sound wave. So in this case, the medium is required for the sound to travel or propagate. But in case of electromagnetic wave, no effect of medium will be there. No effect of medium because they don't need medium. So if the air blows or doesn't blow, doesn't matter in case of Doppler effect of electromagnetic wave. Okay, so with this short introduction, uh, let us go to derive the expression for the relative change in the frequencies in different cases. So what are the different cases? I'll just see. There can be relative motion. So I'll just tell you, suppose this is source, this is observer. So there can be relative motion if the source is moving with some velocity vs, but the observer is at rest. Okay, or if the source is at rest, vs is 0, but the observer is moving, and in both cases v medium I have taken as like still, air is not blowing. If the observer is generally written as O, VO, is moving towards the source or away from the source, then also there will be relative motion. Okay, we'll just discuss today these two cases when the source is moving towards or away from the observer, what will be the apparent frequency, and when the source is at rest but the observer is moving towards or away from the source, then what will be the apparent frequency. Suppose the sound wave has original frequency nu, so what will be the change in the frequency that is observed by or received by the observer. So first case is that we are going to derive an expression for the apparent frequency when the observer is stationary. Observer is stationary, that means VO will be 0. Stationary in still medium means V medium is 0, and the source is moving towards the observer. So this is the case. Okay, source is moving towards the observer. So source has, okay, so let us just derive this. For derivation, if I will just refer this figure, let me tell you that suppose initially the source and the observer, they were at L distance away initially when time does not start. Okay, initially this was the case. Anyway, if you observer is rest, but the source is moving with the velocity vs, and the source is producing a sound which is moving with a velocity v. This v is the, so I'll write vs is the velocity of sound. Okay, with respect to the still medium, obviously v is the velocity, I'm sorry, this is not the source of the sound, this is the source of the sound. Vs is the velocity of the source of sound, and this v is the velocity, okay, I'll not repeat this, velocity of sound wave. Okay, velocity of the sound, and VO refers to velocity of observer. Here it is equal to 0. Okay, this observer's velocity is 0. Now look, suppose nu be the frequency of the wave, sound wave that is produced by the source. Okay, so nu be the frequency which is like frequency of the sound emitted by the source when it was stationary. Okay, and see the observer and both observer and the sound source of sound, if they are at rest, both are at rest, then nu be the frequency which will be observed by or heard by the observer. Okay, nu will be the frequency heard by observer. So that I can write this, if that t is the time period of oscillation of the source of the sound, then this nu is equal to 1 by t. I can write that means after each interval of each, like after t interval of time, the source is actually sending some compression of the wave. Okay, sound wave, compression of the medium actually. Okay, so compressional waves we can say. Now at t is equal to 0, the source is at a distance L and it emits a pulse of the wave, so that will take time. So when the source of sound is at this distance, okay, it just emits a pulse. Okay, emits a pulse. So to reach up to the observer, what will like for the sound has velocity v, so what will be the time taken by the sound? Okay, first pulse of sound wave to reach the observer is given by tu1 is equal to L by V. Why is it so? Because at t is equal to 0, the source of the sound is releasing this pulse. So this wave has to reach all the way up to the observer, and in that process it has to travel a total distance of L. And since it has a constant velocity v in the medium, so the time will be taken by the first pulse to reach up to the observer is this one, L by V. Now suppose at time t is equal to t2 over here. So see, t2 means again is capital T. Okay, t2 means it is capital. So suppose in the it is, I'm sorry, not t2, I'm writing the time t2. So at t is equal to 0, one pulse was released by the source. Another pulse is released just after a time period only. Okay, after the time period, after the time interval capital T, since it is the time period of oscillation of the source of the sound. But by this time, the sound wave has traveled Vs into T distance up to here, right? So what is the remaining distance which the second pulse has to travel is Vs into this. So this much distance the second pulse, this pulse has to travel. So what will be the time taken by? So this is one point. The second point, I'll just go to the next page. So the second pulse will take T2 is equal to L minus Vs by T by V. So second pulse will take T2 is equal to this much second, okay, or this much time. Let us not bother about the unit of the time. So this much time, okay. So second pulse will take this much time to reach the observer. Sorry. Okay. So what is the then therefore the time period of the sound received by the observer will be how much? T prime is equal to T2 minus T1. So second pulse goes by T2 time and first one goes in during time T1. So the difference between these two time will give you the time period of the sound received by the observer. Okay, so this will be, see, first was, okay, this is based by T by V minus, in fact this will be a lesser time. Okay, anyway, this is L by V. Now if we just do a little bit of simplifications, oh no, I'm sorry, this will take T plus of this, okay, T plus of this much time, okay. Second pulse will take actually not only this time, this much time, one time period has been already elapsed, okay, already elapsed, one time period is elapsed, so this is the total time it takes, second pulse. So there will be T over here. So what we get if we just make a little bit of simplifications over here, what we'll get, see, this will be T plus, so L will go away anyway, so these are both same, so you will get T plus so T, this is not plus, this is minus, I'm just doing at a single time, so this will cancel each other, so there will be Vs T by V. Okay, this will give you, suppose T common, V minus Vs by V times T. So this is the time period. So then what is the apparent frequency? If this is the time period, apparent time period, so frequency will be 1 by T prime. So 1 by T prime means V by V minus Vs into T. Okay, or if we, I'm sorry, this will be 1 by T. 1 over t. Okay, so 1 over t means, again, this is nu. I'll write this as nu. See the frequency, now the frequency of the sound wave detected by the observer, stationary observer, when the source of the sound is moving towards the observer, is this. So this is the factor. You can look, this factor is actually less than 1. I'm sorry, this is actually greater than 1. This is greater than 1 means what? So this factor is greater than 1. Okay, let me go to the next page. So we have got, when it is actually, it is away from this, away, I'll be discussing here. Now it is towards the, so source is now going towards the observer. So in this case, okay, when the velocity of this is this, and sound velocity is v, so v by v minus vs into nu. And see, this factor is always greater than, it is always greater than 1. That's why, so which implies that nu prime, the frequency heard by the observer, is greater than the frequency of the sound wave which is originally emitted by the source. Hence the pitch, that's why we can see, hence the pitch of the sound appears to increase, when the when the source of the sound approaches or approaches towards the observer. So when we are in the station sitting over a bench and waiting for our train, when the train comes with certain speed and ringing the whistle, what we see, gradually the pitch of the sound increases. Okay, this is the case. This is mathematically, this is the case. Okay, so nu is equal to v by v minus v. So if you remember, this formula itself will help you to solve the problem. Now we have got this, but when the train is going away, what we see, what we hear, the pitch of the sound decreases. Okay, so when the source is going away from the observer, then what happens? Look, in that case, we'll replace this vs by minus vs. Okay, when the source is going away, with vs, so this is your observer over here, this is source is going away from the observer, so we'll replace the vs with minus vs, so this will be becoming positive. In that case, you look, in this case, v by vs plus v, this factor is always less than 1. It is less than 1. That's why the pitch of the sound seems to be decreasing when the train is going away while blowing the whistle. Okay, so pitch of the sound will be appearing to be decreasing while the source of the sound goes away from the observer. Okay, so this is away from the observer, and here I'll clean things here. Some of the things I'll clean and write the formula. I'll directly write over here. So it will be actually T V minus Vs by V. Okay. So the apparent frequency when the source is coming towards the observer is nu prime is equal to V by V minus Vs into the original frequency. If you remember this formula, remember this V is actually sound of source, sound of velocity of the sound. Okay, so these are the formula. Now we'll go to the next situation where the observer is stationary, but the source is, I'm sorry, the opposite way, like other way. We'll derive an expression when the source is stationary in the still medium, but the observer is moving towards the source, towards or away. Both will find out. First, we'll just check when the observer is going towards the source. What will be the frequency? So to derive that, let us take this figure as our reference. So suppose we consider the case when the source is stationary here and the observer is moving with the velocity VO. Okay, this is observer here, and as usual the velocity of the pulse or the sound wave is V, and anyway Vs is 0. Okay, in this case. So suppose the pulse it 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 creates with the frequency nu. It has frequency nu initially. Now we have to find out what will be the frequency heard by the observer while approaching the source. So at any instant of time, look what happens. At any instant of time, since the source and sound, see, source and the observer, when both are at a distance L away, then before the observer starts moving, suppose it produces a sound wave. It has to travel all the way this L distance, right? Okay, so at any instant, in this case, actually, you have to find out, or you have to remember that at any instant, the separation between the pulse, between two pulses, separation, at any instant, the separation between two pulses is the lambda. Lambda means the wavelength. Okay, wavelength. So this is given by the v times t. T is the time period, and this is the v. V is the velocity of the sound wave. So at any instant of time, this will be the separation between the two pulses. Okay. Now, after t time, suppose when the observer receives a compression pulse, The next pulse is at Vt distance away. Okay, Vt distance away. Next pulse will be at Vt distance away. Okay, so this is Vt distance away. Now the second compression pulse moves towards the observer. See, second one is also moving. That is after time t actually. Time t. After time t, second pulse is created and that is also moving towards this. But by the time it reaches, suppose it is a time period t prime. I'm sorry. Uh, the observer will receive the second pulse after certain time interval. Suppose that is the time period t prime. The sound wave the observer is receiving has time period t prime. That means the second pulse will move this much, whereas the other one, the observer will move VO t prime, and the sum of these two, sum of these two is the distance, okay, and divided by okay, so this is the distance. This will be actually exactly equal to lambda. Lambda is Vt. So at any instant of time, as I said, at any instant of time, the separation between the two pulses will be V into T. Okay, so we know the two pulses, like see the second pulse will reach by this actually. Okay, so that this we can just write. So T prime will be from here V by V plus V observer into T. Okay, now we'll go to the next page. So what we have got, the time period that the time period of the sound that the observer receives is given by T prime is equal to V by V plus VO into T. Now what will be the frequency then? Nu prime will be just reciprocal of the time period. So it will be V plus V by, sorry, VO by V into 1 by T means again frequency. So this is the frequency. As you can see, V plus V naught is greater than V always. So sorry, greater than V. So that's why this factor is again, this implies nu prime is greater than nu. Okay, nu prime is greater than nu. Thus the pitch of the sound appears to increase when the observer moves towards the source. So same thing, if if the observer is moving away from the source, so this is the source, this is the observer. If the observer is moving this way, then this apparent frequency can be written by V minus VO. So this velocity of the observer has to be replaced with a minus sign. So this will be See, in this case, nu prime is less than nu. In this case, this is the case for this, and when the observer is moving away, and this is actually when the observer is moving towards with the velocity. Okay, so I'll just summarize what are the formulas we have learned today. And if so, we'll summarize what we have learned. So when source is moving towards observer, observer has zero velocity, that means at rest, and it has velocity vs, and sound wave has velocity v and frequency nu. So what will be the frequency heard by the observer? Okay, so that will be v by v minus vs into nu. This is first formula we have learned. But if the source is moving away with velocity vs, whereas the sound is going towards the observer, okay, the same velocity of the sound in the medium and frequency also same, and observer is at rest, then the frequency heard by the observer will be v by v plus vs into nu. So you can easily find out that here in this case nu prime is less than nu, and here nu prime is greater than nu. Okay, the frequency appears to be increasing in this case. In this case, frequency is appearing to be decreasing. I'll summarize the other case also. When the source is at rest, doesn't have any velocity, sound have velocity the same, frequency also same, the observer now moving with the velocity VO towards the source. So what will be the frequency? Nu prime will be V plus VO divided by V into nu. Okay. In this case, V plus V no VO is always greater than V, so nu prime will be always greater than nu. Okay, so the apparent frequency or the frequency heard by the observer when he is moving towards the source, it seems to be increasing, but suppose the source is still at rest, sound pulse is moving towards the observer, and observer is moving away from the source. So what will be the frequency? Will replace this velocity over here with a minus sign divided by V into nu. In this case, obviously, the new denominator is greater than this, so here nu prime is less than nu. Okay, so with this we'll stop it here for today. Tomorrow we'll take up the case when the medium is moving with either of the observer or the source. Then what will be the case? When the medium is moving either with the source of the sound or with the observer. In that case, what are the modifications in this particular formula? We'll see in the next class tomorrow. Okay, so bye for today.
This conference will now be recorded.